Vector spaces are where vectors live. Um, so vectors, you can add them together, scale them together. Well, maybe not scale them together, but you can scale them. For example, if we have v as v1, v2, v3, then we have cv1, cv2, cv3. You can add them together. And that would just be that v1 plus I guess maybe naming it a different thing would be better, but each component would be added, and that's pretty obvious, pretty simple. Vector spaces will have certain rules to them, but first I want to go over what is a vector space. I guess we could do but first I want to say, like, what is a vector space? So a vector space, some examples. So we could have R2, which would be the two-dimensional plane, X and Y. We could have R3, which now extends this to a third dimension. And you can keep going on. R4, R5, etc. Vectors here add and scalar vectors add together, and you can have scalar multiplication. But surprisingly, polynomials are also a vector space, which I always thought was really confusing. So polynomials you can add together, like 3x squared plus 2x plus 1. You can add with another polynomial. Even if it's a higher degree, you can still add it together. You could do something like that and then add them together. This would work if we're in P4, because we're in degree 4, so P4 right here. But if we're in P2, which is what this would be, it could also be extended to P4 with 0 and 0 for the x to the 4th and x cubed terms. But yeah, this would be P2. And if we're in P2, this wouldn't be allowed under but this wouldn't be allowed under normal vector spaces rules if we were in P2. But yeah, polynomials are vector spaces. You can add them together, and you can certainly multiply by a constant. Let's say c is equal to 2, then we have 6x squared plus 4x plus 2. Still a polynomial. Another example of vector spaces are functions. F of x. The reason being that if you have g of x and f of x are functions, then you can say we have f plus g of x is also f of x plus g of x, and you can scale it by a scalar. Scalar. Huh. I guess what I have in my notes is c times f of x. And that would be equivalent. So that would be like if you have x squared and you're multiplying by a constant, now you have, say, like 2x squared or 3x squared. But it's essentially just x squared times some constant. And because we're studying in linear algebra mostly matrices, matrices are also vector spaces because you can add them. If you have a is m by n and b is m by n, and we could have c could be equal to a plus b, and that would be the matrices. Let's say we have the identity plus double the identity, and that would be triple the identity. You get the same matrix, well, same size matrix. You can scale a matrix by a constant, and it would still be a matrix of the same size. What isn't a vector space? Well, for example, x plus y equal 1. This is a line in 2-dimension space. So 1, 1. This is not a vector space. We can also have x squared plus y squared equal 1. This is also not a vector space. Let's come back to that. So the rules for vector spaces is closure under addition, meaning if you add two vectors, say u plus v, you get a new vector, w, that is in the space. That is important. It has to be inside the space. For example, let's say we're in R2, and we have 1, 2, and 3, -5. And when we add them together, we get 1 plus 3 and 2 plus -5. Or 4, -3, which is still a vector in R2. Mostly because R2 is all of the entire plane. And then rule number 2 would be commutativity. Commutativity. Basically, if we have two vectors, u plus v, this is equal to v plus u. So you can change the order. There's the associativity, u plus v plus w is equal to u plus v plus w. Identity, meaning that there is a zero vector. So u plus 0 is just u. And then we have the inverse. U plus the negative of u is equal to the 0 vector. And then we could distribute c times u plus v the CU plus CV. Or something like that. And of course, multiplying by 1 is just the same as itself. I don't know why that's important. Alright, let's do an example. So, I know I said the line wasn't a vector space. That's not entirely true. If we have the line y is equal to 2x, this technically is called a subspace because it belongs to R2. I guess even also R3, but I'll do another video on like subspaces, but first we check for the 0 vector. So basically we go 0, 0. Is this on the line? 0 is equal to 2 times 0, which is equal to 0. And that's yes, 0 is equal to 0. Is it closed under addition? So let's say we have u is equal to 1 comma 2 and v is equal to 3, 6. If we add them, u plus v, is that going to be a point on the y is equal to 2x? So that's 4 comma 8, and that is still double 2x. We could scale it by a constant. Let's say c is equal to negative 3. And this is also 2x, y is equal to 2x. So it is a vector space. Or a subspace, I guess you could say. But now x plus y is equal to 1. This is also a line, but it's not through the origin as I drew earlier. It's like that. So does this have the 0 vector? If we say x and y are equal to 0, 0 plus 0 equal 1. 0 cannot equal 1. And just by that, you know, it immediately fails. It is not a vector space. But we can also say, okay, well, if x is 1, 0 and y is 0, 1, is that equal to 1? This is going to be equal to the point 1, 1, but if x plus y is 1, 1, then we get 1 plus 1 is equal to 2, and that is not equal to 1. So that is not closed under addition. And if we have a scalar multiplication, let's say we have 1, 0, the point, and we scale that by 2, we get 2, 0. 2 plus 0 does not equal 1, so it is not closed under scalar multiplication. That's pretty much how you approach these types of problems, or not problems, but this concept of vector spaces.